It is one of the most common questions people ask about aviation, and on the surface it sounds completely reasonable. If a commercial aircraft is in serious trouble, why can't passengers simply put on parachutes and jump out? Skydivers do it routinely. Military aircrew have ejection seats and parachutes. Small aircraft can even be fitted with whole aircraft parachute systems. Yet the hundreds of passengers on a commercial airliner have no individual escape system at all. No parachutes under the seats, no ejection capability, no bailout option. The assumption is that parachutes are a simple safety addition that someone decided not to include. That assumption collapses the moment you examine what deploying a parachute from a commercial aircraft actually requires, and what the conditions inside and outside look like during scenarios where a parachute might theoretically help. The confusion comes from treating parachute use as a straightforward action. Put it on, jump, land safely. That sequence works for a trained skydiver exiting a small aircraft at a suitable altitude and airspeed. None of those conditions apply to a passenger on a commercial airliner in an emergency. The gap between the mental model and physical reality of attempting it from a commercial jet is so large that examining it reveals the truth. To understand the scale of the problem, consider the environment outside a commercial airliner at cruise altitude. The aircraft is flying at 35,000 feet. The outside air temperature at that altitude is typically between -50 and -60 degrees Celsius. The atmospheric pressure is approximately 23% of sea level pressure, insufficient to maintain consciousness in an unprotected human. This condition is called hypoxia. The airspeed of the aircraft is approximately 900 kilometers per hour. At that speed, the dynamic pressure of the airstream is sufficient to cause immediate and severe physical injury. The combination of temperature, pressure, and airspeed means a passenger exiting without specialized equipment would lose consciousness within 10 to 15 seconds. They would experience severe physical trauma from the airstream before any parachute could function effectively. The scenario is not dangerous in the way that jumping without a parachute is dangerous. It is dangerous in a fundamentally different way. The environment itself is lethal before the parachute question even becomes relevant. The most common response to this argument is that parachutes would only be used at lower altitudes during final approach, or after an emergency descent to breathable air. This reframing appears to resolve the altitude problem, but introduces other prohibitive constraints. Scenarios where a commercial aircraft is at low altitude and in trouble are precisely when there is no time for parachute deployment. An aircraft on final approach at 1,000 feet with a landing gear failure has approximately 15 seconds before touchdown. A structural failure at low altitude produces a debris field within seconds. An engine failure or runway excursion leaves no time for preparation. None of these scenarios produce the combination of sufficient altitude, time, and aircraft stability that passenger parachute use would require. When an aircraft is in a stable emergency descent, a normal emergency landing is the vastly superior outcome for all passengers simultaneously. This is compared to a sequential individual bailout that would take many minutes to complete. The physical requirements for parachute use are demanding. A standard deployment requires a minimum altitude of approximately 600 to 800 meters. This allows the canopy to fully open and the descent rate to stabilize before ground impact. It requires an exit airspeed typically below 200 kilometers per hour, so the jumper is not immediately incapacitated by the airstream. The jumper must also maintain a stable body position to prevent uncontrolled tumbling that can prevent clean deployment. Parachutes are not one size fits all. An incorrectly fitted harness can cause the parachute to separate from the wearer during opening shock. This shock occurs at a force of several times body weight. Furthermore, the jumper must execute the sequence under extreme psychological stress. Emergencies may occur in darkness, while injured, and after having received no training. Most passengers cannot be assumed to meet these requirements. The exit geometry of a commercial airliner presents its own constraints. Doors are not designed for parachute exits. They open inward and then slide outward, a sequence requiring significant physical effort and taking several seconds. The door sill is not at floor level. Passengers would need to step up and out into a powerful high-speed airstream. This would occur in a cabin that may be tilted, vibrating, or partially depressurized, making controlled exit extremely difficult. Aircraft doors are certified for emergency ground evacuation, not for sustained in-flight opening at high speeds. At approach speeds, the airstream is powerful enough to prevent an untrained person from even maintaining their position at the door. The logistical constraints compound the physical ones. A narrow-body aircraft like the Boeing 737-800 carries up to 189 passengers. Equipping each with a parachute, sized, fitted, and stowed accessibly, adds mass. A typical sport parachute system weighs approximately 10 to 15 kilograms. For 189 passengers, that is roughly 2,000 to 3,000 kilograms of additional payload. On every flight, carried as dead weight on every sector whether needed or not. The stowage volume required for 189 parachute rigs significantly reduces the usable cabin space. The fitting and briefing process, ensuring every passenger has a correctly sized and adjusted harness before departure, adds time to every turnaround. And the liability and regulatory framework around parachute equipment, which requires regular inspection, repacking, and certification, adds maintenance complexity that the airline industry has no existing infrastructure to manage at the scale of the global commercial fleet. These are not insurmountable problems in isolation. Combined with the physical constraints, they eliminate any operational case for individual passenger parachutes. The comparison to whole aircraft parachute systems, which are certified for and fitted to some light general aviation aircraft, is instructive. The Cirrus aircraft CAPS system, the best-known example, deploys a large parachute from the aircraft's airframe that lowers the entire aircraft to the ground at a survivable descent rate. It has saved lives in scenarios where the aircraft was uncontrollable. But the CAPS system works on a single-engine aircraft weighing approximately 1,600 kilograms at speeds below approximately 185 kilometers per hour. Scaling this concept to a Boeing 737 at 70,000 kilograms or an Airbus A380 at 575,000 kilograms produces parachute canopy sizes and deployment forces that are not achievable with current materials and deployment mechanisms. The parachute required to slow a fully loaded wide-body airliner to a survivable descent rate would be larger than the aircraft itself, and the deployment shock, the sudden deceleration, would impose structural loads that the airframe is not designed to withstand. Whole aircraft parachutes are a viable safety addition for light aircraft. The physics do not scale. The reason commercial aviation is as safe as it is has nothing to do with individual escape systems. It is the result of redundant systems, rigorous maintenance, precise procedures, crew training, and an accident investigation culture that treats every incident as a source of information to be acted on. The probability of a commercial airliner experiencing a scenario where a parachute would have been the correct intervention, rather than the aircraft landing normally under emergency procedures, is extraordinarily low. The scenarios that do occur are overwhelmingly survivable through the aircraft's own systems, the crew's training, and the structural integrity of the airframe. Parachutes would add mass, complexity, and a set of physical and operational constraints that the vast majority of passengers could not meet, in exchange for a marginal benefit in an extremely narrow set of scenarios that the existing safety architecture already handles more effectively. So why don't commercial planes have parachutes for passengers? Because the operating environment of a commercial airliner, altitude, airspeed, temperature, pressure, makes parachute use physically impossible. Without specialized equipment that passengers do not have and cannot be trained to use. Because the scenarios where a parachute might theoretically help are either too extreme for survival or too benign to require one. Because the physical, logistical, and operational constraints of equipping, fitting, and deploying parachutes for hundreds of untrained passengers are prohibitive. And because the safety record of commercial aviation is built on a completely different architecture, redundancy, procedure, and systems engineering, that addresses the actual failure modes of commercial flight far more effectively than any individual escape system could. The absence of parachutes is not an oversight. It is the correct engineering answer to the question of how to keep passengers safe on commercial aircraft. What does the evacuation of a commercial aircraft actually look like when it goes correctly? And what are the certification requirements that determine how quickly all passengers must be able to exit through half the available doors? The 90-second evacuation standard, the research behind it, and the physical constraints reveal how much planning goes into the escape systems that commercial aircraft do have. I have covered that in another video.